Go
Go
ahead.
ahead. Okay, thanks.
Jireh will tell us about operator algebras in Mathlib.
Yeah, thanks. So just some background for people who are not familiar with operator algebras, which maybe it's been a long time since you've dealt with them, or maybe you've not had a course in them yet, or whatever. I'm just gonna give you a little bit of background. So, um, a C-star algebra is a possibly non-unital, complete normed star algebra. So that's just an algebra with an extra operation called star, which is involutive and linear and anti-multiplicative. Um, and the norm satisfies this property called the C star property, that the norm of x star x is the norm of x squared. So the two most canonical examples of C star algebras, the first one is the continuous linear maps on a Hilbert space. And there the star operation is given by the adjoint. And this is sort of one of the canonical examples because every C-star algebra by the Gelfand-Naimark-Siegel construction is isomorphic to a closed star subalgebra of this. So basically you can realize any C-star algebra as being represented as continuous linear maps on a Hilbert space. And on the other side is the example of continuous functions on, we'll say complex valued functions on a compact Hausdorff space. And here the norm is given just by the sup norm. And these are also sort of a fundamental example because it turns out that every commutative C-star algebra is star isomorphic to such a space of continuous functions. Okay, and so you have these two sort of main examples which sort of encapsulate everything. Now, in fact, this identification between commutative C-star algebras and these continuous maps, it's actually an equivalence of categories. And so for that reason, oftentimes people refer to C-star algebra theory as non-commutative topology, because in the commutative case, you have this equivalence of categories. Okay. So just as a little bit more background, we can refer to the spectrum of an element in an algebra as just the things for which the values of R in the scalar ring, such that R times 1 minus A is not invertible. And that's the spectrum of an element A. And it turns out that the spectrum is, a key thing to look at. In the case of, say, matrices, this corresponds exactly to eigenvalues and so forth. And so there's this great fact, which is that if A is a normal element, that is, if it commutes with its star, then the star subalgebra generated by that element is commutative. And so as a result of that equivalence of categories I mentioned, you get that there's this identification with the continuous functions on the spectrum of A into the complex numbers. And so from this, we get to something called the continuous functional calculus, which is just this this map from those continuous functions into the full algebra A. A lot of times we denote this by f of A, where f is the function and A is the element, but it satisfies this. The important part about it is not just that it's a star algebra isomorphism, it's also that it satisfies this compositional property that G composed with f of A is G of f of A. Now, this is kind of weird because on the left side of that, this is all about a continuous functional calculus. So on the left side, that's an application of a star isomorphism for continuous functions on the spectrum of A. And on the right side, it's two different star isomorphisms. The F1 is we're applying a star isomorphism to F, and F is continuous on the spectrum of A. And then G, we're applying a star isomorphism to G, which is a continuous function on the spectrum of f of A. Okay, so there's this this compositional property that you need to satisfy. Okay, so let me just give you some of the background on the progress that we've made so far in C-star algebra theory and Mathlib. So about a little less than 2.5 years ago, Frederic introduced C-star algebras, the definition of C-star ring, into Mathlib. And, you can't really get anywhere before you define that. And, you know, relatively quickly, we had, a few instances. The two that I mentioned already as examples, continuous linear maps and continuous maps. And then we got some other ones, in particular, what's called the multiplier algebra of a C-star algebra. This, if you think about the equivalence of categories that I mentioned between commutative C-star algebras and continuous maps, the multiplier of a C-star algebra corresponds to the stone-check compactification of the space that you're dealing with. So it's, in some sense, the multiplier algebra is the largest C-star algebra that contains your original algebra as an essential ideal. So, it's kind of a complicated construction. Unfortunately, right now we can't do much with it, which I'll explain later. Basically, it's because of our lack of non-commutativity and our lack of non-unitality in our definition of ideals right now. And then in addition, we have the unitization of a C-star algebra. So this is the smallest unital C-star algebra containing a given one. Now, this construction, when the algebra is non-unital, it adds a multiplicative identity to it. But when the algebra is unital, it adds a new multiplicative identity to it. So this has some nice functorial properties, which is why it gets looked at a lot. But it does this kind of weird thing of creating a new multiplicative identity if you already had one. Oh, and just as of yesterday or the day before, I put the operator norm on matrices, of course, in a scoped instance, not globally, but now we have matrices as a C-star algebra as well, if you want it. So some other things that have happened, just defining basic objects, self-adjoint elements, unitary elements, normal elements, the character space of an algebra. We said the unitization. At some point, we had to define star algebra homomorphisms and all this stuff. Interestingly, this one, I just recently defined non-unital normed commutative rings, and this is actually made possible only by Lean 4. Of course, this is sort of tongue-in-cheek, but the issue was that in Lean 3, I just hit way too many timeouts. I could never get all of Mathlib to compile because it was just totally screwing with type class inference. And in Lean 4, there was a small hit, but it wasn't large, and so we were able to put that in. So now you can actually talk about non-unital commutative C-star algebras, which we couldn't before. And then this unitization star lift, it's just the universal property of the unitization. It says if you have any non-unital algebra and a non-unital algebra homomorphism into a unital one, then you can raise it into a unital algebra homomorphism from the unitization. Okay. But then we've also got a lot of spectral properties so far. And this list is actually really made possible only by the work of everybody, especially Yuri, on the complex analysis library, because this stuff is just not possible without things like Liouville's theorem. So we of course define the spectrum, but then got a bunch of basic properties in Banach algebras for it, but including Gelfand's formula. But really a key one, so Gelfand's formula definitely uses the complex analysis in an essential way, and also proving that the spectrum is non-empty also requires complex analysis in an essential way. So, a lot of these are properties that are just sort of in the first chapter of a book on spectral theory or of a book on operator algebras, but it relies on a lot of stuff before it. And to be honest, I'm not sure which, if any, other proof assistants have a definition of or these theorems in spectral theory, because I'm not sure. I think probably HOL's or Isabel's the only one that has a large enough analysis library in order to do it. I could be wrong. So some key theorems that we've got. We do have that the Gelfand transform is a bijective isometry, or in fact a star algebra isomorphism for C-star algebras. And the other major thing we have the Gelfand measure theorem, and we also have spectral permanence and the continuous functional calculus. So let me explain kind of what those things are. So spectral permanence, also known as why I need Mathlib to be non-unital. If you've spent much time with me or talking to me, you'll realize that I kind of go on a lot about how we need to make Mathlib a lot more non-unital. And in the past months, I've, devoted some time to developing just basic API for non-unital structures, non-unital sub-semi-rings and sub-rings and subalgebras and star subalgebras and all this stuff. It was a big chain of things that we had to build, but pretty boring, but at some point it has to be done. But the reason that we need it to be non-unital is because of this theorem, which we have in Mathlib, and it's called spectral permanence. And it says that if you have an element in a unital C-star subalgebra, its spectrum inside that small subalgebra is equal to its spectrum in the big algebra that contains it, right? And so actually this property is the thing that allows you to talk about the spectrum of an element in a non-unital C-star algebra, right? This is sort of a weird concept because the spectrum, right, it's the set of values in the scalar ring such that r times 1 minus your element a is not invertible, but that wouldn't make any sense in a non-unital algebra because there is no unit, so you can't even talk about inverses, right? So the interesting thing though is that in C-star algebras it doesn't matter, because all you do is you take your non-unital C-star algebra, you embed it in any unital C-star algebra, and then you look at the spectrum of your elements in that bigger unital algebra. And the point is, it doesn't matter which one you choose, because the minimal unitization embeds into all of those. Okay, and so this gives you a coherent notion of spectrum of elements in a non-unital algebra, and then you can do spectral theory with those things. Okay, so it's been a big quest to make Mathlib non-unital, and meanwhile, Christopher Hoskin has had a parallel quest in which he's trying to make Mathlib non-associative. So if you haven't seen that, he's been working very hard doing that, and the PRs have been kind of a lot. They get a lot of comments, and it's challenging. So I want to compliment him on that. Okay, so what is this continuous functional calculus? So we actually have a version of the continuous functional calculus in Mathlib already, and it is exactly this algebra, the star algebra isomorphism that I said before, right? That the continuous functions on the spectrum of A with values in the complex numbers, that's isomorphic as a star algebra to this elemental star algebra. This is just the C-star algebra generated by A. Okay, it's the C-star subalgebra generated by A. Now, there's a few things about this. If you then take the embedding of this star subalgebra in the big algebra, you get that isomorphism that I talked about originally. So from continuous functions to the algebra A. And that's what we call the continuous functional calculus. And in particular, you get some equalities, right? So the range of a function, well, that's exactly equal to its spectrum viewed as an element of this algebra, right? So that's just the spectrum of F. But because this is an algebra equivalence up here, that's actually the spectrum of its image, right? It's the spectrum of its image In which algebra? In the elemental star algebra. Okay, in the C star stub algebra generated by A. But by spectral permanence, that coincides with the spectrum of A in the big algebra A itself. Okay, and so we actually get this nice little fact that for the continuous functional calculus, the spectrum of the image of some element under the continuous functional calculus is just equal to the range of the function on the spectrum. Okay, and we get this rule for the composition property that you need G to be like F has to be continuous on the spectrum of A, but G has to be continuous on the range of F. Okay, now there is something that you'll notice here if you're paying close attention, but I wouldn't expect you to catch right away, is that we've just wandered into like the 7th or 8th level of hell or something in terms of dependent type theory, because lots of things depend on other things here. In particular, we're talking about functions defined on continuous functions from a subset of the space into C, and also the continuous functional calculus itself depends on the value of A, little a, in the big algebra A. Okay, so we have the continuous functional calculus, that star algebra equivalence that I gave before, but we don't have like an API that makes the continuous functional calculus available yet. And why is that? Basically, the reason is dependent type theory hell. That's part of it. We need to come up with an API that either avoids this or sidesteps it enough that it's not a problem. Another issue is that this only works for the complex numbers, but maybe we want a continuous functional calculus on self-adjoint matrices with real entries or something like that. Another big issue is, well, this requires a C-star algebra, which means you need a norm, but things like matrices don't have a norm. And so, as is, we couldn't just apply this continuous functional calculus to matrices. There's the issue of non-unital algebras. This equivalence that I gave only works for unital algebras. And then there's the issue of we want to be able to talk about a continuous functional calculus not just for normal elements, but for self-adjoint elements or positive elements in your algebra as well. So there's a lot to juggle, and making something that is continuously or is going to manage to simultaneously solve all of these problems is very difficult. I have a PR, but I keep going back and forth about what the right way to do it is. So let's talk about that just a little bit. So in the current version, I'm creating a new class for a continuous functional calculus, and this is just going to it's going to be a star algebra homomorphism from the continuous functions on the spectrum into the full algebra A. So not into the subalgebra, but just into the algebra A. And it's going to have a few properties. It's going to be a closed embedding. It's going to have the property that it sends the identity function to A. And it's going to have this property that I mentioned before, that the spectrum of the image is just the range of the continuous function F. Okay. So the nice thing about this definition is it allows for doing things over other scalar rings, or other scalar fields. So the real numbers as well, but also even the non-negative reals, if we're worried about positive maps on positive operators and things like that. It doesn't require a norm structure. We just have topological considerations here. And then there are some disadvantages. One, it's not going to handle non-unital things at all. But in addition, that's not such a big deal, because I think that just should be a separate thing anyway. We're probably just going to have to deal with the non-unital case separately. But the big one is that we're still in dependent type theory hell. This class, the CFC class, it depends on the value of little a. And also the functions themselves depend on A as well, because they're continuous maps from the spectrum of A. And so you can see this is just, kind of a recipe for headaches. Now, I managed to get around them for the most part, but there was still issues. So, I've considered some alternative things. One is we could just not include the star algebra homomorphism as data, because actually that star algebra homomorphism is uniquely determined by those three properties. And then you don't have this data. You can sort of have this class just give you this star algebra homomorphism that's uniquely determined. And it's uniquely determined by the Stone-Weierstrass theorem, basically. Another way is to remove the dependent type in the class by not defining it for a specific element of A, but by defining it on some predicate like is star normal or is self-adjoint. And then so this would be a class that takes a predicate and then gives you a star algebra homomorphism for everything satisfying that predicate. And then the other option to really help with the dependent type hell is to talk about continuous functions, not on the spectrum, but just on the full scalar ring R instead. And actually, and then the condition would be you'd have to add the condition that if two functions are equal on the spectrum, then their images under the star homomorphism agree. And this would remove the dependent types from the domain or from those continuous functions. And that would be perhaps quite handy. It's a little bit more work, or it's sort of a lot more work because then you have to apply TC extension to get the original restricted star homomorphism back, which presumably you would want from time to time. So, yeah. So, that's kind of where we are. Hopefully, relatively soon we'll actually have a working API for the continuous functional calculus. That's definitely number one on my agenda to do. But if you are interested in contributing to this at all, there's a lot of work that still needs to be done. We definitely need to continue making Mathlib non-unital. We also need to deal with this issue of two-sided ideals, and this has been discussed on Zulip a number of times, but I actually provided a link here to a GitHub project that lists sort of the items that we need to get done in order to make that happen. Because really, after the continuous functional calculus, two-sided ideals are the next big stumbling block to getting operator algebras off the ground in a really serious way. Of course, we'll want to get a version of the continuous functional calculus for non-unital algebras. And then, I would say like a really major milestone to say we've sort of arrived at a nice place is getting square roots of positive elements. Now, this is sort of important because this precisely uses the continuous functional calculus. Like, how do you get something that's a square root? Well, if it's a square root, it has to satisfy this property. But if you think about that, the way you show that this identity holds is you apply the continuous function square root on the spectrum, and then you apply the continuous function squaring, and those two things give you the identity function, which gives you A back. So it fundamentally uses this compositional property, and it also does it on positive elements, which is kind of an extra hurdle that you have to jump through because by default we're only getting the continuous functional calculus on normal elements, and so we have to get like a restricted version for positive ones. So another thing is we have a definition. I spent all this time talking about C-star algebras. We have a definition of von Neumann algebras in Mathlib, but we have zero API for it. So if this is the kind of thing you're interested in, that's another place that you could be contributing. So yeah, thanks.
Okay, thanks a lot for that talk. So I see a question by Patrick, I guess.
Yeah, hi. So thanks, Jireh, for the talk. So first, maybe a remark. So you mentioned that it was crucial to have a complex analysis in Mathlib, but maybe for people who are far away from that kind of mathematics, we could point out that you need complex analysis in a huge generality, not like complex analysis for functions from C to C. So it's nice to know that we have infinite dimensional complex analysis and integration and stuff.
Yeah,
And,
indeed. Definitely having it for Banach spaces was absolutely crucial.
yeah, so finite dimensional is not enough. Yeah. And the question is, so you kept saying that non-unital is important, but then all the examples of C-star algebra that you showed were unital. So what are the examples of non-unital algebras that you care about?
Oh, sure. So I mean, yeah, it's a good thing to point out. The fundamental non-unital examples would be the compact operators on a Hilbert space. And that would be like the canonical non-commutative example. It's fundamental in a very crucial way. And then also just continuous functions on a locally compact Hausdorff space. So then you don't have an identity element because you don't have the constant function 1. Sorry, I said that incorrectly. Continuous functions vanishing at infinity on a locally compact Hausdorff space. Again, with the supremum norm. So, but yeah, there's lots of others. But you know, when you're doing C-star algebra theory, the really interesting stuff happens in the interplay between the unital and the non-unital theories.
Thanks.
Question by Kevin.
So how far away are we from two-sided ideals? That's obviously completely independent of continuous functional calculus, right?
Yeah. I mean, I think it's probably not that bad. I don't know if you can see this. It's probably too small.
Yeah, I can see. Yeah. Oh, that's better. Yeah.
Okay. So the answer is it shouldn't be actually too bad. I mean, I think the big one is this make algebras have right actions without diamonds. And I know that Eric has thought about a lot about that, and he even had a PR in Mathlib 3 which rotted. So yeah, but I think really the answer is we're not going to go through bimodules at all.
So currently our solution for right actions is left action of the opposite, right?
Yes, but we don't. When you have an algebra instance, you only get a left action. It doesn't imply a right action automatically. Because if it did, we would get diamonds. I don't remember exactly what the diamonds are. Eric would know the answer to that.
I mean, is it actually worth making a new right action? Would this be a ridiculous thing to do?
The more time we spend, the more I think this is going to be the way we do it in the end.
Oh, that's interesting. Who just said that? Is that
Anatol?
Oh, okay, interesting. You think that's what's going to happen in the end? Because we have this completely heterogeneous multiplication now, right? And somehow Mathlib has randomly chosen this A to B to B to be special and develops a huge amount of theory, but it's no different to B to A to B, is it really? We just need to think of a new notation.
We have the notation now. We have notations for left and right actions. That's a tiny step towards.
Oh, but is that right? But is it just really a left action by the opposite?
Yeah. But at least it looks good now. That's
yeah, but that doesn't solve the key problem, which is just that if you actually.
Of course. I'm not saying this is a
silver
bullet, but you also need good notation.
Yes, indeed.
And then we would perhaps need some tactic that just generated all the right action lemmas from the left action lemmas.
Yeah. I mean the problem right now is just that you get diamonds unless you add a bunch of new fields to all these structures. That's the issue.
Yeah. So in a different direction, how far are we from Gelfand duality? Like this equivalence of categories that you mentioned.
I think we actually have it. Hold on, let me see if I can find that real quick. I mean, at least for non or for unital algebras, I think we have it. So let's just.
Oh, there are 2 new questions now. So.
Okay. Well, go ahead.
Anatol, yeah, you can show me on Zulip. So Anatol.
Yeah, I just wanted to say a huge thanks to Jireh for doing all this non-unitalization thing, because like I've been postponing starting to work on operational algebras in Mathlib for like at least a year, and like I'm happy that this stuff is being done because like it's a huge amount of non-interesting math that needs to be done behind the scenes before we can do interesting things. So thanks a lot.
Yeah, thanks.
And Sophie, final question?
I was just going to ask, how far do you think we are from GNS?
So I thought about this a long time ago, and then I've just been trying to focus on the continuous functional calculus primarily. I think GNS wouldn't actually be too hard. The biggest issue is that we don't really have ways to talk about positive linear functionals yet. So that would be the theory that you would need to develop, is the theory of like self-adjoint functionals and then positive functionals. But after that, it's really not too bad. I don't think it doesn't require any of the other stuff. So the key thing is just getting the cyclic representations, but that just I don't think it should be that hard. But I just haven't put in the time to working on positive linear functionals yet.
Cool. Thanks.
Okay, thanks a lot again for these nice talks, and well, that concludes today's